Hello, we start another week in this journey of understanding polymers, and in this week we are going to focus on viscoelasticity in polymers. And the words viscoelastic and polymers are almost synonymous. So much of what we know about viscoelasticity is because we had to describe all the phenomena which are associated with polymeric materials. So, whenever we say viscoelastic materials, the first material that comes to mind is polymers, and it is the specific macromolecular nature of polymers and the fact that there are so many different time scales and length scales in polymeric material that we cannot ignore viscoelasticity in polymeric materials. Many other materials and especially engineering materials, we could ignore the viscous effects and treat them as elastic materials, or many times we ignore the elastic effects and treat them as viscous materials. However, in case of polymers, in the solid state we cannot ignore the viscous nature, in the liquid state we cannot ignore the elastic nature. So, that is why viscoelasticity is synonymous with polymers. So, in this week when we are going to focus on the phenomena of viscoelasticity, we will introduce some of the concepts in this lecture, and one of the things that you will notice is the field of viscoelasticity is extremely interesting from the point of view of how it explains the real behavior of polymeric system. At the same time, it is also reasonably complicated. Now, what do I mean by complicated? Because we cannot ignore either the viscous or elastic effects. Everything depends on what is the question we are asking. Everything depends on what is our point of interest. So, therefore, it is not just a material which is viscoelastic. The type of viscoelasticity and the type of viscoelastic behavior shown by the material would depend on what is the engineering application in mind, what is the scientific time scale of interest. So, based on that, then we can understand viscoelasticity. So, we will introduce the topic of a viscoelasticity by again focusing a bit more on all these related aspects: time, temperature, the rate of change of quantities, or frequency, which is again a rate of change of quantities. And one of the conceptual way in which we highlight this issue of material time scale and experimental time scale is using Deborah number. So, we will quickly look at what can we learn from understanding Deborah number and its magnitude. So, the viscous response and elastic response, the molecular view is that in case of elasticity we have storage, and that is because the atomic and small molecular solids, there is deformation, displacement and recovery. And because of this, of course, we have said several times that only the current state of both stress and strain are important. The rates are completely irrelevant. It also does not matter whether 10% strain is reached after 5% or after 15%. In the sense, I can apply 5% strain, then increase it to 10%. I will observe one stress. I can go to 15% strain and again come back to 10% strain, again I will observe the same stress. So, history rates are completely irrelevant, because what really matters is only the displacement of the atoms and molecules, because it is the secondary interaction between atoms and molecules which is overcome in terms of displacing, and the secondary interaction is only dependent on distance between molecules. So, therefore, as long as distance between molecules is fixed, so at 10% it is one value, at 5% it is less, at 20% it is more. So, therefore, stress is completely defined based on strain. However, like we saw in the lecture 43 on plasticity, that if phenomena such as twisting, unentangling, orientation, slippage, if such phenomena happen, then clearly we will not have this issue of stress being independent of history, because then it depends on how the slippage happened, how the orientation happened, and so the current state is important, but what is equally important as how was current state arrived at. Viscous response on the other hand is completely dissipative response, and here of course for small molecular liquids or atomic liquids, the idea is molecules are completely randomly anyway going about, and then when we impose a stress on the material starts flowing, and as it starts flowing it continuously dissipates energy because molecules can randomly go about impinging on each other as they are moving also on an average. So, therefore, there is a continuous dissipation of energy, and molecular order anyway does not get affected because anyway it was randomly impinging on each other. They continue to collide and bombard each other as well as the walls of the container or pipeline wherever they are flowing. And so, in this case, because a steady state is always reached in terms of when we apply a constant stress, we always reach a constant strain rate. So, the current state of stress and current state of strain rate are what are valid. So, if you look at Newtonian fluid as an example, you can see that stress is proportional to strain rate. Here in this case also, the rate at which energy dissipation happens does not depend on what happened in the past or how did you arrive at the steady state. So, if let us say shear rate in this case is 5 per second, it does not matter whether it was flowing much faster earlier or it was sheared at 100 per second earlier. 5 per second determines the stress, because the current rate of dissipation completely depends on what is the rate at which molecules are being displaced with respect to each other. So, in case of elasticity, it is only the displacement which counts. In this case, since the displacement is happening continuously, molecules are randomly going around and flowing, it is the relative rate of displacement between molecules which leads to dissipation, and that is what matters. So, this is a molecular view in case of let us say small molecules. So, now if we have a macromolecular system, what can be the features, and that is something for us to think about. So, what happens when we have a macromolecular material? Now, when we have let us say a small molecular elastic solid system, amorphous solid, it mostly happens to be amorphous solid. It will deform little bit and then break. So, because up to some extent atoms and molecules can be displaced, beyond a certain point crack will start. But in case of macromolecules, even in the glassy state, not all molecular motion is frozen. So, it is possible for chains to unentangle, it is possible for chains to twist, and so therefore, we cannot really consider macromolecular systems to be elastic under all conditions. In the rubbery state, in fact, conformational changes are easily possible. So, subsegments, side groups can rotate with respect to each other, and segment themselves can also change conformations. So, clearly this is more a liquid like system where there is random motion of molecules possible. However, in the rubbery state, the overall macromolecule cannot move, but only parts, segments can move. And so, therefore, a rubbery state seems to have properties which are associated with solid as well as liquid state, and therefore, it also is viscoelastic. In the molten state, in the liquid state of macromolecules, now there is sufficient thermal energy for whole molecule to also move about, but one macromolecule is entangled with another macromolecule. So, even though this whole molecule, of course, segments can move about, because let us say for PET, melt temperature is 250, molding happens let us say at 270 degrees Celsius. Of course, these macromolecules can move about, the segments also can certainly move about, but the motion of macromolecules is hampered because of the entanglement which are there. And so, if you look at a segment, it is almost like it is stopped or anchored at two locations due to entanglement with two other chains. So, it is as if there are temporary junctions in the polymeric molten material, and these between these junctions the segment can stretch and again can recover. Recovery implies elastic response, because material can go back to its earlier state. And so, segments in molten state, because of entanglements, can also recover. So, elasticity is there in the molten state. So, that is the fascinating aspect of dealing with mechanical response of polymeric system, that in the solid state we still have to worry about molecular movement, chain orientation, chain untwisting, and in the molten state we have to worry about elastic recovery. So, therefore, viscoelasticity is always important whether we are worried about glassy state, rubbery state or molten state of polymers, and that is why at the beginning of the lecture when I said that viscoelasticity and polymers are synonymous, now you can see how macromolecular nature, how closely it is linked to the behavior of viscoelasticity. So, let us look at viscoelasticity in little more detail. So, basically viscoelasticity means that we have both viscous and elastic response. However, the relative contributions will vary depending on the time scales of interest. And this is what I meant when I said in the beginning of lecture that viscoelasticity can be complicated, and the reason is this, that it depends on the time scale of interest. So, therefore, for certain design of engineering polymers, we may be able to assume elasticity because that is the time scale of interest that we are working with, and those are the numbers with which we will do our design. Does not mean that the material itself may not be showing some viscoelastic aspect, but the overall practice of engineering and technology happens in such a way that we can get away by assuming elastic response. Same thing is true about, let us say, transport in huge pipelines of materials which are non-Newtonian or viscoelastic fluids. Again, there we can assume that they are largely viscous fluids and again get away with engineering empiricism. However, that does not imply that the viscoelastic melt itself is not showing any viscoelastic behavior. So, this quantification of how do we assess whether viscoelastic effects are important or not is done using a hypothetical number called Deborah number, which is a ratio of the experimental or the engineering time scale of interest, and which is also basically the experimental time with respect to the relaxation time of the material that we have discussed several times. So, the relaxation time is the characteristic of polymeric material. Of course, we know that there is not a single relaxation time in polymer. There is relaxation time associated with side group, there is relaxation time associated with segment, there is relaxation time with overall macromolecule. So, of course, we have a relaxation time spectrum in the material, but in general when we want to think about what is the relation between the material time scale and experimental time scale, what we need to look at the ratios of these two. And if Deborah number is very small, it implies that either lambda is very small or experimental time scale is very large. And generally while introducing topics of viscoelasticity, we talk often about example of from geology, and geological time scales are basically lakhs and crores of years, millions of years. So, therefore, in those time scales even plate tectonics and geological basically deformation that happens on the earth's crust surface, the models can be viscous fluids or viscoelastic fluid like models. So, that is the idea behind Deborah number. So, if our time scale of interest is so large, then the viscous phenomena, the dissipative phenomena will start happening, and something like a rock which for a few seconds or hours or even hundreds of years seems like a solid object, over crores of years seems like a fluid like object. And so, opposite case is there when we have Deborah number much greater, in which case now the experimental time scale is very small or the relaxation time of the material is very large, which is the case let us say when we observe the rock for a 5-year or 10-year period, because in the time scale associated with the material itself is extremely large compared to the experimental time scale of interest. And so, generally when we are analyzing the viscoelastic response, it is helpful sometimes to look at the terminal response. What do I mean by terminal response? We can look at either a short time or a long time response. We can say that okay, polymeric melt material has certain aspects of elastic recovery due to segments and entanglements, but if I make the polymeric melt flow very slowly, then it ought to show certain amount of viscous behavior which is dominant, and therefore I can ignore elastic response. So, therefore, terminal response of a polymeric melt under extremely slow strain rate conditions will be a viscous response. We can also think in terms of polymeric solids, that if I do an extremely fast experiment where I apply the load, the polymeric molecules do not get a chance for untwisting or conformation change or any of the features which are associated with dissipative response. So, then a polymeric material, which even if it has segmental mobility at room temperature, if I do the deformation extremely fast, then none of the segmental mobility will be relevant because deformation is done so fast. So, then the material would appear to be elastic. So, therefore, terminal response is always useful for us to guide in terms of can we see the extremes of behavior, the viscous dominating behavior or elastic dominating behavior as we change the conditions. So, I already explained about rate or time of observation. We could also do the same thing if we are doing a sinusoidal loading. Then if we do a very fast sinusoidal loading, then we are basically not giving material enough time. So, it is associated with small time, high frequency, or very low frequency, which is more gradual, implies that we are giving material sufficient time. So, generally low frequency response will be viscous like and high frequency response will be elastic like in a viscoelastic material. So, let us just look at this question from exam to try to discuss little more about elastic response, viscous response and viscoelastic response, and how it is a matter of time as to which one of these will be more dominant. We will soon define an experiment where we try to look at viscoelasticity in a material by doing creep and recovery experiment. So, we apply a constant stress on the material and then we remove that stress. So, if you were to just look at what is the experiment and look at what is happening to a stress as a function of time. So, at time t is equal to 0, a constant stress is applied, and after certain time suddenly that stress is again brought to 0. So, this part of it is called recovery and this part of it is called creep. So, because this application of the stress, the material starts deforming, and so we measure strain as a function of time. So, this question is asked where plot of strain versus time for a polymer is given, and based on this plot we have to find whether we have viscoelastic deformation happening, elastic deformation happening, is there a recovery which is viscoelastic or is there a recovery which is elastic. And so, what we need to think of is what would happen if we had a completely viscous material in this experiment, or what would happen if we have a completely elastic material in this experiment. So, if we assume that this is the load which is being applied, now what would happen in case of elastic material, which is let us say a Hookean elastic material. So, clearly strain in this case as a function of time, because the load is constant, strain will also be constant, and in fact this strain will be equal to sigma naught by E, which is the modulus of the material. And as soon as we remove the load, again strain will fall to 0. So, this is strain as a function of time for an elastic solid. You can look at this similar analogy you can do for a viscous Newtonian fluid, and what you will be able to show is that strain will increase linearly during creep, and when the load is removed there is no recovery in the material. So, you can think about how to arrive at the shape that I described and rationalize how the response for a Newtonian fluid would look something like this. So, now we can look at the graph and then you can try to see whether there are elements of both of these responses in this creep and recovery test. And you can see that yes, it neither looks like elastic nor looks like viscous, but it seems to be a combination of the two, and that is the characterization of viscoelasticity. And that is why, for example, creep, which is a dynamic test because time is involved, is used to characterize viscoelasticity in the material. The question that I have been trying to emphasize is viscoelasticity depends on the conditions under which we are observing the material. So, the same sample, polymer sample, let us say, which is shown in this graph, instead of doing experiment over the time whatever is given here, what if I do it at very short amount of time. So, instead of applying stress for let us say 1 minute or 2 minutes, what if I apply for microsecond and then leave it. So, I take the material, apply stress for a extremely small amount of time and then leave it. Will I observe an elastic response? For example, will I see, because the strain is being applied for a very short amount of time, creep is being applied for a very short amount of time, will I see strain? Pretty much like an elastic solid. Think about it. On the other hand, if the creep experiment is conducted for years, what is the response that we will see? So, therefore, depending on different times, the same polymeric material may show different behavior, in the sense that elasticity may dominate when we do creep and recovery for very short amount of time, and viscous nature will dominate when we do creep and recovery for much longer periods of time. What if we change the temperature on the material? So, let us say if this is nylon and this experiment was being done at 45 degrees Celsius, now the temperature is changed to 65 degrees Celsius. So, about 20 degrees Celsius higher. So, what can we expect in terms of creep and recovery? So, because the temperature is higher, we would expect that strain to be more, but is qualitatively also anything changing, and what will be the response of the material? And so, clearly when we change the temperature, what are we changing with respect to material? We will keep the time the same. So, the experimental time scale now remains the same, but because we have changed the temperature, the relaxation time in the material changes, and so again therefore Deborah number changes. Now, we could also if we are not applying a constant stress, if we are applying strain rather than applying a constant strain, we could apply a constant strain rate. More importantly, as we are doing many of these viscoelastic experiments, we have to be careful while what can be done in reality and what we draw for some simple understanding in the beginning. So, for example, I talked about the stress being manipulated this way, where we say that stress as a function of time for creep and recovery, initially it is sigma naught and then it is brought down to 0. So, how does it go from at time t is equal to 0 to sigma naught? A real instrument will always do this in finite amount of time. It is not going to happen at time t is equal to 0 and immediately the stress becomes 0, gamma 0, so sigma 0. So, it has to actually take certain amount of time before it can reach sigma 0. So, the rate of increase of stress is an instrument feature, and therefore, two different instruments in which you do this creep and recovery experiment, if the initial rate of increase is very different in the two cases, you will get a different response, because the rate of change of stress in the beginning period is also important. So, therefore, rate of application of stress or rate of removal of the stress, each of these can be features which will influence the viscoelastic response, and that is what one really needs to understand, that viscoelasticity depends a lot on how we are looking at the material response. And so, dynamic testing and looking at time, temperature, rate variations are very crucial when we look at the viscoelastic behavior in much more detail, and that is what we will do in the 47th lecture. We will look at the type of dynamic tests which are used to characterize the viscoelasticity. So, with this we will close this lecture. Given that constant stress is applied in creep and elastic response is basically instantaneous deformation as we saw earlier. So, I am sure all of you can then try to get the answer, because for a viscoelastic material, strain would increase first and then it would become constant. So, this is an elastic feature that it becomes constant, while increasing implies it is a viscous behavior. So, as we will see later on, Voigt model, which is one of the simplest model to describe viscoelasticity, predicts in fact an exponential increase in strain. So, with this we will close this introduction on viscoelasticity, and in the next set of lectures we will start defining quantities which can characterize viscoelasticity as response variables. Thank you.